This is Form A from the warm-up quiz that you guys took, the little FRQ quiz that you took after your multiple choice quiz on Friday. There are 4 forms. I'm going to go through them one at a time, starting with Form A. If you didn't have Form A, you're welcome to skip past this and look at Forms B, C, or D, and I will put that in the description of the video, the timestamps that you can jump to. However, it is obviously still beneficial information, so if you want to watch all 4 of them, then by all means you can do that. Form A says the following circuit is found inside one group's electric house. Calculate the equivalent resistance of the circuit. So we'll start with part A. And so this is a combination circuit. I know that because I have a parallel section and I have a section that is in series with that. And so we have both components to consider here. When you're trying to find equivalent resistance for a combination circuit, you need to figure out the equivalent resistance for this circuit anyway, for this parallel section, because this entire parallel section is in series with this. And so we're going to start with that parallel section, figure out what that is equivalent to, and then we'll be able to add it in series with our 50 ohm resistor. For the parallel section, we're going to treat this like we would any other parallel equivalent resistance calculation, and we're going to use the formula for a parallel circuit. Our equations are right here for circuits, and we're going to be using this one that has all of the fractions in it because we're dealing with a parallel section. So for this first one, for the parallel part, I would have 1 over 60 plus 1 over 30. And that's going to give me 1 over RT for the parallel part. This isn't going to be our final answer. It's just going to give us the equivalent resistance for that section. You're welcome to do this in a calculator or by hand. This is easy enough because 1 over 30 would be the same thing as 2 over 60 if I doubled both of those, and that makes this whole thing 3 over 60. Okay, again, you'd want to get a common denominator. 1 over 30 is the same thing as 2 over 60, and then you'd have 1 plus 2, and that's where the 3 came from. But again, this number right here is not equal to RT. It is equal to 1 over RT. So once you get it, you're going to flip that fraction and get the reciprocal. And that's going to be 60 over 3, and that would be equal to RT, which of course is 20 ohms. Again, this isn't your answer. This is the equivalent resistance for this entire parallel section. So this section is 20 ohms, and this section is in series with a 50 ohm resistor. So when I go to find the total resistance of the circuit, we're simply going to add together the 20 ohms that we have for the parallel section plus the 50 ohms that we have for R3, which is in series with that section. That gives us a total resistance for the circuit of 70 ohms, and that is your answer. Now you are welcome to organize this information into a table. So if you want to create one of those tables that we used in class, then by all means please do so. It's not provided on the space, but you do have the back of the sheet, and maybe you chose to do that. If so, cool. If not, it's not a big deal. Unless I ask you to fill it in, you don't have to. Part B says which of the resistors above spends the most voltage, and then how much. If they're tied, list all of them. So I know that whenever I'm looking at spending voltage, I'm looking at voltage drops. This is a combination circuit, and so I know that in this circuit I have 2 different loops. And again, it does help, in my opinion anyway, to color code those loops. So some of your charges are going to be following this green loop here on their way back to the battery, and the other charges in the circuit are going to be following this purple loop on their way back to the battery. Okay, in either case, on both of those loops, you have 2 different resistors that your charges are traveling through. On the purple loop, they travel through both R1 and R3, and on the green loop, they travel through both R2 and R3. If you recall, we talked about Kirchhoff's laws, and we talked about how the voltage drops along a loop add up to the battery. Okay, in a parallel circuit, we didn't have more than one on a loop, and so we were able to say, hey, these are both equal to the battery. That is not the case here. Okay, Okay, in this particular circuit, because each of them has 2, whatever voltage drop happens here has to add with this for the green loop to equal 14. And whatever voltage drop happens here has to add with this for the purple loop in order to equal 14. Now, there's a couple different ways you can approach this. If you want to solve for those voltage drops, you're going to either need to figure out what the current is, and then use that current along with the resistance here to figure out the voltage drop here, and then this would be the other one. So that's one way to do it. The other way to do it is to deal with it in terms of proportional reasoning. This entire section here, if you recall, has an equivalent resistance, which makes it equivalent to a 20 ohm resistor. Again, we calculated it up here. So this is equivalent to a 20 ohm resistor. This is a 50 ohm resistor. Again, we have a total of 70 ohms. So you can treat this as a proportion as well. And it is a little bit faster if you want to try to do that. We've only done a couple of examples like this in class, but if you wanted to figure it out, you would have, this would be 20 out of a total of 70. So figure out what that is as a percentage or a decimal. But 20 over 70, and that would be, give you a percent, obviously it's less than half. And then you could multiply it by the total voltage, because the voltage is going to split proportionally according to the resistance. So if I do this, 20 divided by 70 is about 28.6%, 0.2857. And then I just multiply that number times 14. Again, this is one way to do it. And that gives me a voltage drop of 4. So this total resistance in this section gives me a 4 volt drop. On the other hand, this is 50 out of 70. And so we would have 50 out of 70, figure out what that is as a percent or the decimal equivalent, and multiply that times the 14 volts. Again, I'll show you the other way as well, but 50 divided by 70, and then multiply that times 14, and that's 10 volts. So this gives a 10 volt drop, and look at that. This and this add up to this, which they should. Okay, and so you can do it that way. So which one spends the most voltage? Obviously 10 volts is greater than 4. Each of these has a 4 volt drop. They are always the same as each other. Even in the combination circuit, they're just not going to match the battery because they have to add with this. But my resistor that spends the most voltage is R3, and R3 spends 10 volts. And so that would be the answer here. Again, your other option is to figure out the total current in the circuit. So let's talk about how we would do it that way. We're going to get the same answer, but I just want to show you in case you feel more comfortable with that, or if you're filling in the table, then this would be part of that process of filling that in. So again, the total current in any circuit is going to be found by Ohm's law, V equals I times R. The total voltage in any circuit is the battery. So we're going to use 14 volts, and we're going to use the total resistance that we found in number 1. And so if we do that, we would have 14 equals I times 70, meaning that 14 divided by 70 would give us our current. So the total current here, leaving the battery, is 0.2 amps. Now that 0.2 amps is going to split over here. But again, these two voltage drops are the same, and what I would recommend that you do first is solve for this one. Okay, it's easier than messing with that. So again, if I wanted to use V equals I times R, I know the total current goes through here. I can see it, purple and green both. I'm going to use my total current, 0.2, and I'm going to use the resistance right here, 50. Okay, and that'll give me the voltage drop at that one. So 0.2 times 50, and look at that, it's the exact same number. It's still 10 volts. Okay, and again, because the voltage drops have to add up to 14, if this is 10, then each of these has to be 4. Because on the green loop, you would have 4 plus 10, and on the purple loop, you would have 4 plus 10. Okay, and so that's another way you can find it. If you're filling in the table, that's the way you'd be doing it, but it is possible to solve this with proportions. All right, letter C says draw a voltmeter on the circuit which will correctly measure the voltage of that resistor. Okay, it's talking about the resistor right above, R3. So you should have drawn a voltmeter that measures the change in the circuit around R3. And so your voltmeter should look like this. It should be connected in parallel around the resistor. You didn't have to draw it right around it. If you put one here and then one here, it's the same thing. Again, you just need to make sure that the resistor falls in between it and that you're not measuring more than one resistor. So something like this in parallel, connected to either side, just like we did in class. And then part D. What is the power through that resistor? Again, power has the equation V times I. Okay, so we would need to know the current and the voltage, and we already found the current. We've got it right there. If we hadn't found it earlier, we would need to find it now. And so you would take your voltage, which at this resistor, that voltage drop is 10 volts. And so you would have 10 and then times 0.2. And that would give you your power. Now, if you multiply 0.2 times 10, that's going to be 2 watts. And that would be your answer for the last one. So again, that's how you would solve all of Form A for the quiz. Let's go ahead and take a look at Form B. And then we also will have C and D after this. All right. So for Form B, it says the following circuit is found inside one group's electric house. So different circuit. It is still a combination circuit though, because I have R2 and R3 are in series and they're in parallel with this. And so anytime you have series and parallel connections, you are dealing with a combination circuit. This one is a little different. When you calculate it, you will first need to figure out the total resistance on this branch so that you can then figure out what it's parallel with to get the total. So you're still going to have to do a series calculation and a parallel calculation, but you're doing them in the opposite order as compared to Form A. And so if I wanted to figure these out, again, the series calculation's easy. So that's going to be R2 plus R3, which is 100 plus 500. And that makes it 600 ohms. So on this branch, my total resistance is 600 ohms. But again, that's not the total circuit. I now have to add it in parallel. When you do the parallel calculation, again, you're going to be using the equation for calculating equivalent resistance in parallel. That's this one with all the fractions. And so when we go and do this, we will have 1 over 600 plus 1 over 400, because that is in parallel with this, and that will be equal to 1 over RT for the circuit. Again, when we add these, you need a common denominator. You're welcome to get them both out of 1200 if you want, or you can do this in the calculator, but this is going to become, if I make this out of 1200, it'll be 2 out of 1200, plus this one will be 3 out of 1200, giving me 5 out of 1200. Again, that's not your answer. That's equal to 1 over RT. So get the inverse, flip that fraction. And when you do that, this becomes 1200 divided by 5. And that's how you go about getting your equivalent resistance. So we'll go ahead and put that in the calculator, or you can do it in your head. But 1200 divided by 5 is 240. And so the equivalent resistance here is 240 ohms. All right, part B. Which of the resistors above receives the most current? How much? If they're tied, list all the resistors. Okay, so I do know that my current will split according to the resistances on each branch, and I do know that my current will prefer the path of least resistance. So since the total resistance on this branch is 600 ohms, I do know that this one will have more current going through it. But since I don't know the total current, I need to get that first. Okay, this one, I don't have the little shortcut to do the proportional reasoning because I actually have to find the total current. Again, if I want to find the total current, I'm going to use the total voltage and the total resistance. We got the total resistance in part A. So again, V equals I times R. We're going to use our battery's voltage, 24 volts. We're going to use our total resistance, which is 240 ohms. And we're going to use that to find I. So that's going to become 24 divided by 240, which you can do in your head or put in the calculator. Either way, we get that our total current is 0.1 amps. Again, the question doesn't ask for the total though. It asks for which resistor receives the most current. So I can actually answer that before I do any math. I know I'm going to have more current through R1. Again, it will prefer the path of least resistance, and 400 is less than 600. So I know it's R1, but how much is it? Again, now you can split it proportionally now that you know what the total is, or you can just go back to Ohm's law. Again, Ohm's law is V equals I times R. Again, in a circuit like this, I know that if I color code my loops, which would be a good idea, I know that the voltage drop along a loop adds up to the battery's voltage. So I know that this 600 ohm resistance, the equivalent resistance there, will create a voltage drop. And I know that on this purple loop, there's only one resistor to create a voltage drop. Okay, but each of them is on a separate loop. This is on the purple loop, so its voltage drop, treated like a parallel circuit, it's going to be 24 volts. This voltage drop, you would calculate, or actually no, it's going to be 24 volts. It has to be. Okay, now they're going to add together to be 24, but the total is going to be 24 volts. Okay, and so I already know it's this one, so I know that oh, it's not asking for voltage drop though, sorry, it's asking for current, so I can calculate my current now. Okay, you need the voltage drops to do it. On this one, you would need to figure out how much of it goes to each place. If you needed those, you don't actually need those, so we're going to go here. Again, I'm trying to figure out my current here, so I would do V equals I times R again, using my 24 volt drop, and then I times, this time just the 400 ohm resistor, and so 24 divided by 400. Which is 0.06. Okay, so the current going through there, so current at R1, 0.06 amps. Okay, and that should be the most current. Let's see. The other way that you can go about doing this, if you wanted to figure out, these are going to receive the same amount of current here because they're both on the green loop. If you wanted to figure out how much current they receive, you could do the same thing and have 24 divided by 400, or sorry, not 400, 600 for that one. Take that back. And each of those would be 0.04. Okay, again, 0.06 plus 0.04 gives me my 0.1. They'll add up to the total. But for this one, it's here. You could also solve this with proportional reasoning and do it that way if you prefer. Since you know the total resistance, 400 versus 600, you could split it according to that. All right. Next one says, draw an ammeter on the circuit which correctly measures the current through that resistor. Again, it's referring to this resistor that we picked up here. It's referring to R1. So anything that just measures purple, again, since that's the color I used for this one, so I could draw that ammeter right here. I could draw it up here. I could draw it down here. Anywhere where it's just purple, make sure there's no green. Okay, but it does need to be drawn in series, which means it's part of the circuit, so draw it on the wire. The last one says, what is the power through that resistor? Again, the power equation is V times I. Okay, I know the current through there is 0.06. I know the voltage drop, so that's all we need. 24 times 0.06, and that's going to give me my power through that resistor. Again, if you're putting this into that table that we used in class, you could also see it organized really nicely that way, but the power that we get here is 1.44 watts. And that is Form B. Okay, so again, A and B were given to first through fourth period, and then fifth through seventh period had either Form C or D. So let's take a look at C and D now, starting with Form C. Okay, so Form C is actually the same circuit that we saw earlier. Okay, we saw this in Form A, but there are different questions being asked about this circuit. So it says calculate the total current through this circuit. In order for us to calculate the total current in this circuit, we need to know what the total resistance is. So even though we're not asked to find the total resistance, we need to find the total resistance. Again, in order for us to do that, we need to recognize, hey, this is a combination circuit, and we need to treat this whole parallel section, figure out what the equivalent resistance of that is, and that section is in parallel, or in series rather, with this. So if I'm trying to find my total resistance, I have to start with a calculation for the parallel section. And that's going to be 1 over 60 plus 1 over 30. Again, this is the formula. It's on your formula chart for parallel. It's right here. It's the one with the fractions. Okay, I'm not going to write 1 over 30 though. I'm going to write 2 over 60 so that I have a common denominator, since 2 over 60 is equivalent to 1 over 30. That gives me 3 over 60, which again is equal to 1 over RT. So if I want RT, I need to flip that fraction, 60 over 3, which means 20 ohms is the resistance for this parallel section. Again, we're not done. That's just the parallel section. We have to add to it this, which is in series. 20 plus 50 means that the total resistance in this circuit, 20 plus 50 is 70 ohms. Again, that is not what we're asked to find, but in order for us to solve for what we are asked for, we need that. Okay, if I want to find the total current in my circuit, I need the total resistance and I need the total voltage. The total voltage is right here. Okay, so we're going to go back to V equals I times R using the totals. Now you could redo the table that we used in class to organize everything and look at that total line at the bottom, and that would be okay too. So I have here 14 equals I times 70. And we're looking for that total current, which we're going to find as 14 divided by 70. So 14 divided by 70 gives me a total current I of 0.2 amps. And that would be the current leaving the battery. Of course, it's going to split at this node. Some of it goes here, some of it goes here, comes back together, and we have the total. And again, if you have a combination circuit or a parallel circuit, please draw in your loops so that you can see that. Okay, one of the loops looks like this. Sorry, I didn't draw that very neat. But one of them does this, follows that path. The other loop, on the other hand, is following a different pathway. Yes, there is overlap. Anywhere where you have both green and purple, you're measuring total current, but it does split, and you have a section that's just purple and you have a section that's just green. That may come in handy. So I do recommend color coding your loops for any parallel or combination circuits. But the answer to letter A rather is 0.2. The next question says, which of the resistors above spends the most power? How much? Again, power is equal to voltage times current. Okay, so if I wanted to figure out which one has the most power, I would need to figure out where I have the most voltage and the most current. I can see where I have the most current. I have the most current right here, because right here it's both. So if that also happens to have the most power, most voltage drop, then it's also going to have the most power. Again, this whole parallel section, we already found it earlier to have a 20 ohm resistance. That was this calculation right here. So we're comparing 20 ohms versus 50 ohms. You will get a bigger voltage drop when you have more resistance. So R3 is the answer. I don't have to actually solve the math to know that. R3 will have the most power because it has both the most current and it has the largest voltage drop. Now if I want to actually solve it, since it says how much, we do have to do that. We're going to multiply our voltage we're going to use our power, we're going to multiply our voltage drop times our current. Okay, which means we need to know what the voltage drop is. If I want to find the voltage drop here, I have to use Ohm's law first. Again, Ohm's law is V equals I times R. If you're doing the table, you'll be filling all of this in anyway, and then you can just use those values from the table. But since I don't have a table on my paper, I'm just doing this one step at a time. My total current, which is what flows through here, purple and green, was 0.2. So 0.2. My resistance here is 50. Okay, and so that's what goes in, and that's what's going to give us the voltage drop. So 0.2 times 50 is going to give us a voltage drop of 10 volts. So my voltage drop here is 10 volts. That's not my answer. I want power. Power is voltage times current. I just found my voltage. It's 10. I know my current. It's 0.2. We're going to multiply 10 times 0.2, and when we do that, we are going to get 2 watts. And that would be your answer there. Okay. Part C says draw an ammeter on the circuit which will correctly measure the total current of the circuit. So this is asking for something different than the morning forms did. The morning forms asked for this to be drawn at this resistor. This is asking for total. Hopefully you read that carefully. And so my total current would be measured anywhere where I have both the purple and green lines. So I could draw that here, or up here, or right here. It doesn't matter. Pick a spot. But it does need to be drawn on the wire because it is measured in series. And so I would have my ammeter, for example, at this position right here. Lastly, we have Part D. Part D says describe what would happen to the overall voltage, resistance, and current in this circuit if R2 were removed and replaced with empty space. So basically, hey, what happens if we get rid of this resistor? Well, if we get rid of that resistor, then now we only have the purple loop, which means R1 and R3 are now in series with one another. Okay, when you do that, when you have it and you're comparing a series circuit, you removed one of your pathways. This current for the parallel section was 20. Well, guess what? Now it's 60. Okay, and so in doing that, in removing a resistor from parallel, we are going to cause the resistance to increase. Okay, the resistance is going to increase, and when that happens, it's going to cause the current to decrease. Okay, so more resistance means less current. The voltage, on the other hand, is determined by the battery. We're not affecting the voltage at all. Okay, and so voltage is unchanged or stays the same, whatever you want to write, but your voltage would stay the same. However, you would increase your resistance because you removed a pathway, and that would cause your current to decrease as a result. So that's Form C. All right, we got one left. Let's go ahead and take a look at Form D. All right, here is Form D, and it has the same circuit from the morning version, Form B, but again, we're being asked different questions about it. It says calculate the total current through this circuit. Again, in order for me to find total current, I have to get total resistance. I can see the total voltage here. You're welcome to organize your data into a table like we've done in class before, or you can just do it step by step. Again, finding that total resistance, this is a combination circuit. I have a section here where I have two resistors in series with one another. We're going to figure this part out first. These two in series with one another, add them together, would have an equivalent resistance to a single 600 ohm resistor. And so this branch is 600 ohms, this branch is 400 ohms, but now we're dealing with just a regular seeming parallel circuit. And so if I wanted to find the total resistance, I would use my equation for total resistance in parallel. 1 over 400 plus 1 over 600. Again, you would have to add those two pieces together first to get the total for the branch. And then you're using the parallel equation. So that's going to give us, again, if we wanted a common denominator, 1200 would be it. This would become 3 over 1200. Oops, plus. This would become 2 over 1200. Which gives us 5 over 1200, but again, that's equal to 1 over RT, so we need to flip that fraction, and that gives us 1200 over 5. Again, you can put that into the calculator. 1200 divided by 5 is going to give me an equivalent resistance of 240 ohms. Again, that's not what the question asked for. It wants the total current. So now that we have the total resistance, we can use Ohm's law. Ohm's law says V equals I times R. If we want the total current, we need the total voltage and the total resistance. Total voltage, total resistance. We plug them in. We have 24 equals I times 240. To solve for that current, that means we're doing 24 divided by 240. You probably don't need a calculator for that. Your total current is equal to 0.1 amps. And that's your answer to letter A. All right, letter B, which of the resistors above spins the most power? Again, power has this equation, voltage times current. So we would need to know what our voltage drops were, and we would need to know what our current is. Again, anytime you have a parallel or a combination circuit like this, I'm going to recommend you draw in your pathways so you can see the different loops that the charges are flowing on. Some of your charges are following that green loop, but some of your charges are on this purple loop right here. Okay, and so that's important whenever we start trying to analyze this. So this is always a good first step. The power is, again, voltage times current. And you can see, since we have these two parallel branches, that your voltage drops along this branch is the same as your voltage drops here. So the power is your voltage times your current. You also know that your current is going to split, and that your current is going to split according to the path of least resistance. And so if we were to take a look at what that means, it means you're going to have a greater amount of current through R1 because this is 400 ohms, as opposed to what you're going to have here through R2 and 3 because those together are 600 ohms. So I know that I'm going to have a greater amount of current here. I also know that I'm going to have a greater voltage drop here. Because this is a parallel circuit, the voltage drop that occurs at R1 will be the whole 24 volts. This whole thing will also be 24 volts, but of course only a portion of it would occur at each of these, and these two would add up to 24. So if I'm looking for where I have the most power, it will be the place where I have the most voltage and the most current. Again, that's going to be at R1. I don't even have to do math to do that or to know that. But if I want to solve for that power, again, it's going to be voltage times current. I would need to know how much current goes through here. So before I can actually solve for power, we need to solve for current using Ohm's law. V equals I times R. My V here is 24. I'm looking for the current, and the R is 400. And so if I want to solve for that current, it's going to be 24 divided by 400, which I'm going to put in the calculator. And that's going to give me a current of 0.06. So on my purple loop, my current is 0.06 amps, which I can now use in this equation along with my voltage drop, 24 volts. So if I wanted to solve for the power at R1, it's going to be my 0.06 amps multiplied by my 24 volt drop, 1.44, and so the power there is going to be 1.44 watts. Part C says draw a voltmeter on the circuit which will correctly measure the total voltage of the circuit. Again, it's asking for total voltage, so we can just measure across the battery. Okay, a voltmeter does need to be connected in parallel. And so your voltmeter should be drawn something like this, in parallel outside of the circuit across the battery. Some of you drew it connected here and here. That's fine. It's still measuring that plus some wire in between. But as long as you are measuring across the battery, you should be getting the correct voltage. Just make sure you're not connecting it past this point and past this point. So you could have done those points, that would have been fine, or anything in between, but it needs to be on either side of the battery in parallel. And then lastly, we have Part D. Part D says, describe what would happen to the overall voltage, resistance, and current in this circuit if R2 were removed and replaced with pure wire. So what happens if we do that? Okay, well, if we do that, the total resistance along this branch becomes just 500. So it reduces the total resistance here along that branch. And so that's going to cause the total resistance of your circuit to go down. It is going to cause, in turn, the total current of your circuit to increase. Again, if you have a decrease in your total resistance, your current is going to be larger as a result, and your voltage will be unaffected because the voltage is determined by the battery, which we did not change. It is not determined by the resistors in between. Okay, so that's how you should answer Part D. Again, you can go back and watch the other parts of this, but these are the answers for Form D rather. for the quiz, the FRQ quiz from Friday.